Module 4 is about the Fourier series and the Fourier transform. You should be following it in chapter 7 of the book and Appendix A toward the end of the book. Now in Module 4, we'll be looking at this document here and working through that. But I also want you to download, as soon as possible, these 3 zip files and unzip them and place them in ImageJ images. Now this video, the first video in this series, is about spatial frequency and the frequency domain or the Fourier domain. If we look at the book, chapter 7, page 195, an alternative to looking at images in the spatial domain, which we've been doing up until now, is to look at them in the frequency domain, or we can call it the Fourier domain. Now, previously, we think of frequency for signals whose amplitude or intensity, which is the square of the amplitude, whose amplitude changes with time. And in this case, frequency is the number of peaks or crests of the wave that pass a certain point in 1 second. We use the symbol frequency f, usually small f, and it's measured in cycles per second, the number of cycles that pass a point in 1 second, or hertz, which is the same unit. And that's equal to the inverse of the period of the signal, the period or the repeat time of the signal in seconds. So we use a small f and a large t. Now, our images generally don't change with time. We're looking at a single image. We're going to consider distance instead of time. And the frequency that we're thinking about is the spatial frequency. This is how frequently the brightness changes per unit distance. We're going to call it sometimes the frequency, but the full term is the spatial frequency. We're going to use a symbol small k, and the spatial frequency, sometimes called the wave number, but we'll generally call it the spatial frequency, is the inverse of the repeat distance instead of the repeat time. And if the distance, the repeat distance or the wavelength, is measured in centimeters, then the unit for spatial frequency is 1 over centimeters, or centimeters to the -1. If we look at image J and open up these 2 images, which you'll find in sine images. Open up sine 25H and sine 50H and make duplicates of them. If we take this image, the horizontally changing sine wave, you have to prove that it's a sine wave. If we hold the shift key down and draw a horizontal straight line and then go to analyze plot profile, we'll see that the profile is a sinusoid. So this is a sine wave. It's not moving with time, but the brightness is changing with distance. It's changing. These are the crests. These correspond to the white parts, and down here corresponds to the black pixels of 0 value. So the grey is going from 0 to 255, from black to white, but it's going sinusoidally. The first question is, what's the wavelength of this image, of this pattern? And we see it from the profile. The wavelength is from here to here, or here to here, or here to here. It's the repeat length. And we see along here, distance, it's 50 pixels. It's not calibrated directly into centimeters or millimeters, but it's 50 pixels. So the wavelength is 50 pixels. The spatial frequency is the inverse of that. Spatial frequency k, or k sub x, it's in the x direction, is 1 over lambda, the wavelength in the x direction. So it's 1 over 50. 50 pixels was the wavelength. 1 over 50, or 0.02, is the spatial frequency in pixels to the minus 1. 0.02. If we look at the other sine wave, and again holding down shift, plot a horizontal line and go to analyze, plot profile, we see that its brightness also changes sinusoidally, but its repeat distance, or its wavelength, is, according to this scale, is 25. And therefore its spatial frequency is the inverse of that. The spatial frequency of this pattern is 1 over 25, or 0.04. Twice the frequency, twice the spatial frequency of this, 0.04. This is a higher spatial frequency. This is a lower spatial frequency. Now, there's something special about sine waves. Sine waves are the only shape that have a single frequency. They're pure waves, repetitive pure waves. If we look at another image, you don't have it, but I have it in here, this one called repetitive.tiff, and open up, we see that it also is a repetitive wave. You know, there's something changing. The brightness is repeatedly changing. And let me draw another horizontal line through that and look at the profile. Analyze, plot profile. We see that the pattern of brightness is changing with distance. But this wave here is not a pure sine wave. It's got this more complicated shape. So it's not a single frequency shape. And we'll see, in fact, later that it's made up of 2 frequencies. Or you can do this yourself. You can make this wave here by adding the sine 25H and the sine 50H in image calculator, add them to make a 32-bit result, and then change that 32-bit result back to 8-bit, and you will get this here. And you should save it, call it something like repetitive, save it, and try looking at the profile, and you get this here. It's a complicated or more complicated shape. It's not a simple sinusoid. But the Fourier series, which we'll look at in the next video, the Fourier series says any shape, no matter how complicated it is, any shape can be built up from pure sine waves.